So in this chapter, we want to really focus on making use of diagonal forces. I say diagonal because in year 12, a lot of the forces we worked with were either vertical or horizontal. We came across vectors which represent diagonal motion. There is some horizontal and vertical component to every diagonal vector, to every diagonal force. And we really need to be able to introduce and identify those components. As you can see, I'm taking effort to make a good representation of the diagram I'm going to be working with. Lots of labeling and annotation is still to come, so I recommend that you make a large diagram, or at least a medium diagram that we have space to add our components onto. I'm going to insist that you do a diagram for every question that we respond to. We will come up against exam questions that don't have any diagram, and we have to interpret fully the context that we're working with. So once again, a large scale diagram to show exactly what we're working with. Now, each of these forces can be modeled as a right-angled triangle. And if we're trying to find the horizontal and vertical components, that's the same as finding the adjacent and the opposite within a right-angled triangle. And we know we can use SOHCAHTOA right-angled trigonometry to do that. If we're looking for the opposite, we can use the sine function. The sine of the angle equals the opposite over the hypotenuse. And we can rearrange that to say the opposite should equal the hypotenuse multiplied by the sine of the angle. In this case, the horizontal is going to the right and the vertical is going up. The horizontal is the adjacent, so it should be the hypotenuse times cosine of the angle. The vertical is the opposite. It should be the hypotenuse times sine of the angle. And that's how we should be able to quickly generate expressions for these components. Once again, hypotenuse sine of the angle, since we're working with the opposite, and hypotenuse cosine of the angle, we're looking at the adjacent. On this third force, we have an unknown angle. That's fine, we can still label these. So for the opposite, it's p sine theta, also an unknown force, and p cosine theta. All right, we'll do some problem solving with these to find what these missing values are. Well, we've been told that the particle is in equilibrium. So first, let's try and resolve horizontally. All of the forces to the right should equal all of the forces to the left. So let's just write that expression. 100 cosine 30 plus p cosine theta should equal 140 cosine 45. Okay, it's a good place to start. Let's maybe make the unknown the subject of this equation. P cosine theta, 140 cosine 45, and we'll subtract the 100 cosine 30. Okay, let's go ahead and resolve vertically. Okay, so the particle's in equilibrium, so it's also vertically in equilibrium. All of the forces up should equal all of the forces down. 100 sine 30 plus 140 sine 45 is going to equal p sine theta. All right, we've already got the p sine theta as the subject. What can we do with cosine and sine? Sine over cosine equals tan. So let's do some division and see if we can produce a tan expression. So tan theta is going to be p sine theta over p cosine theta. Okay, and I'll just speed up this bit. But if we just punch this into our calculators, we'll get tan theta, and we also get theta equals 85.25 degrees. We can substitute that into one of our earlier equations. We'll go for the p cosine theta. To find p, I'll just divide the right-hand side by cosine of the angle we've just found, and that gives us a p-value of 149.5 newtons. So once again, we've used our strategy of resolving vertically and horizontally to find unknown angles and unknown forces. Okay, well, let's look at an example that isn't quite problem solving, but does have multiple steps to it. Okay, so here's an example where we have two forces and we want to try and find the resultant force. Not just the resultant, but its magnitude and direction. So we'll start with these two forces, P and Q. Angles are as given, 30 degrees and 45 degrees. Now, each of these forces can be broken into its components. It's horizontal and it's vertical. And let's actually get magnitudes for P and Q. 10 and 8, so we can get our expressions. Here, 10 sine 45. And the horizontal, I've got space, 10 cosine 45. Second force, break it into its components. We get 8 sine 30 and 8 cosine 30. Okay, now that that's fully labelled, let's actually try and find the resultant force. So the horizontal component is going to be made up with these two, 10 cosine 45, plus the 8 sine 30. They're both moving in the same direction towards the right. And for the vertical, I've got two opposite directions. So I'm going to be subtracting the 8 sine 30 from 10 sine 45. Okay, just punching those values into the calculator, making sure we're in degree mode. And we get 14.0 and 3.071. So that's the resultant vector. We can sketch that and label it for its horizontal and vertical component. And yeah, this is a question that we're very used to. We should be able to find the magnitude and the angle for this vector. Its magnitude is going to be found using Pythagoras. And the angle, which I'll label theta, can be found using trigonometry. Okay, so inverse tan of the opposite over the adjacent. And that should lead to the angle of 12.372 degrees. And to be specific, we can say that that is above the horizontal or above the x-axis. So we know that it's not underneath or below that horizontal.